Okay, so we are starting our library of functions, aka parent functions and piecewise defined functions. So our objectives here are to be able to graph the functions listed in the library of functions. Again, that's just your parent functions. And to analyze a piecewise defined function. So we're going to go over what are relatively new, quote unquote, to college algebra parent functions, but are really not new to you. For example, our square root of x, our square root of x, square root function. Okay, so the square root function, the domain of the square root function has a restriction. It's all non-negatives. So that means x has to be greater than or equal to 0. The x-intercept is at 0, which means that the y-intercept is also at 0. F of x is neither even nor odd, and is increasing on an interval from 0 to infinity, and has an absolute minimum of 0. That means that's the lowest the parent function goes, right? So if you remember the parent function, it goes like this. Remember that guy? Starts at 0 and heads towards infinity. So that's our square root function. Okay, you only need to write this down if you don't remember the square root function or any of its properties. But for the most part, I think we're pretty good on the square root function. Okay, we've also reviewed the cube root function. And the cube root function, the domain is all real numbers. The x and y-intercept is at the origin, so it's at 0, 0. It is an odd function, and that's because it's symmetric with respect to the origin. That means there's rotational symmetry. And it increases because we leave from left to right, from negative infinity to infinity. It doesn't have any local max or min, so no local extreme. All right, so we're going to analyze this guy. All right, so we're going to talk about the cube root function. So for the cube root function, basically, if we were to create a table to come up with and graph it, we are looking for, we're going to be utilizing your smallest perfect cubes. Does that make sense? Because that's where we would find our roots. So for example, we would start with -9, -1, 0, 1, and +9. That's because the cube root of -9 equals -3. The cube root of -1 equals -1. The cube root of 0 equals 0. The cube root of 1 equals 1. And the cube root of 9, that is not right. That's supposed to be 27. I'm tripping. Should be 8. Ding dong. Hold on. Lo Santo. Those 8s were never meant, those 9s were never meant to be there. They were supposed to be 8s. Fixed it. You never saw anything. All right. And so these are our smallest perfect cubes. So then when we plot them, we can easily see what happens. So -8, 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to go down 2 and bam. And then -1 and -1 goes to -1, 0, 0, 1, 1, and then positive. 1, 2, 3, 4, 5, 6, 7, 8, and then up to 1, 2. All right. In my defense, I just got through talking about the square root function, and I was just talking. And there is your cube root function. Okay. So when we look here, we can easily see that our intercept is at 0, 0. Can we all see why this is an odd function? And it's with symmetry with respect to the origin. And was it terrible to produce the graph? Okay, do we understand why we used our smallest cube roots? Yes, so realistically be able to plot it, you need to use the smallest values. Now, would you want anything other than the smallest? No, because then you're working with decimals and your graph is going to be a little sketchy. Get it? Yeah. All right, absolute value. So the absolute value, the domain of the absolute value function is from negative infinity to positive infinity because it's all real numbers. The range, however, is y has to be greater than or equal to 0. That's because what's the whole purpose of absolute value? No negatives, to produce positive results. Okay. The x-intercept and the y-intercept are at the origin. It is an even function. That's because it's symmetry with the y-axis. And it has two intervals of activities happening. From negative infinity to 0, it is decreasing. And from 0 to infinity, it is increasing. And it has an absolute minimum of 0 at x equals 0. Are we ready to graph it and talk about it? Here we go. All right, so we want to determine if it's odd or even or neither. And we've already stated what it is, but just to show you, x, y, we can start with some small values, -3, -2, -1, 0, 1, 2, and 3. The absolute value of -3 is 3. Absolute value of -2 is 2. Absolute value of -1 is 1. 0, 1, 2, 3. Because absolute value is essentially just asking how far is the number from 0, right? And distance is always positive. So when we sketch it out, we end up with a V shape. This V shape has two lines. We have a negative slope on the left side and a positive slope on the right side. And our intercept is at 0, 0. And that's why we said it's decreasing and it's increasing. Questions about the absolute value paired function? All right. So putting it all together, all the functions by now that you should know and be comfortable with, you have your constant function, which is just a horizontal line. You have your linear, AKA your identity function. You have your square function, AKA your quadratic. You have your cube function, your square root function, your cube root function, your reciprocal, also known as your rational, and absolute value function. All of these should look and sound very much familiar to you. Okay. A new one that we're going to introduce is the greatest integer function. Okay. How the greatest integer function works. It's based on literally rounding to the nearest integer for the most part. So when you look here, what we have graphed here is our greatest integer function. Notice how this one rounds down because our greater values are not included. So this is also called, there's two types of greater integer function. We have what's called the floor and the ceiling. So if you want to take a stab at it, the floor is going to round down and the ceiling is going to round up. Literally in the calculator, you can type the word floor in most calculators, especially in Desmos. And then you would put in X and it would graph it, okay? But it's just making sure you understand that that means you're rounding down. So if you look here at the table, it says that if x is -1, so if I go to -1, I'm going to have -1. True. If x is -1/2, so if x is -1/2, I'm going to go to -1. I'm at -1. -1/4, doesn't matter. I'm still only at -1. So each one has its interval of where those values are being set. That's why if you look right here, interval, integer, interval, all goes together, okay? When you are looking on the calculator, it literally looks like steps. So sometimes it's called a step function, sometimes it's called the greater integer function, but the reason being is it looks like steps. If your calculator is in connect mode, it really looks like connected steps. If your calculator is in dot mode, it's just regular old little lines, okay? But as you travel, it'll tell you error when you get to certain values that are not defined. And that's pretty much it for the greatest integer function. In your calculator, clear my calculator, 2nd plus 712. I go to y equals, go to math. Is it, which one is it? Oh, there it is. INT, X, and I hit graph, and there it is. And then I can, I believe, to turn off the connect. Can't remember how to turn off the connection right now, but yeah, INT. And it's the integer. So if you go look at the table, you won't see the values in between, but if you turn it on to where it's ask, you can then see how it rounds down. So if I put in a half, what should I get as my answer? If I have a half, I should get 0 because it's going to automatically round down. If I have 0.99999, what should I get? Because it's going to round down. Okay? And that's your integer function. And again, to access it in your calculator, it's math, number, and you should see INT. Okay, as the calculators get updated, the number of words actually at may change. That's why I say focus on what it is, not pressing a number, but looking for INT. All right, questions, comments, concerns? Okay. I need the calculator to go away. Go away. All right, moving on. So then the main thing of it is our piecewise defined function. Our piecewise defined function is where we take pieces of functions and put them together. Hence the word pieces, okay? You have what I call breaking points, and the breaking points is where these two functions separate. So for example, your breaking point depends on your interval. So here, this function is from the left of 1, and this function is to the right of 1. Do we see that? Because it says greater than or equal to. So this is the left and this is the right. So at 1, I'm going to draw a little dashed line for me. On the left-hand side, I'm following this function. And this function has a slope of 2/3 and a y-intercept of 1. So I'm going to go to 1. I'm going to follow the slope, which is rise 2 over 3, 1, 2, 3. But I'm not going to really mark it because it's on the left-hand side. I just need to know where I was going. Here, I have another, I'm going to go down, 1, 2, 3, down 2, 1, 2, 1, 2, 3, down 2, 1, 2, 3. Okay, I know that this point is roughly at 1 2/3. So at about 1 2/3 on this graph, I have a hole. And the reason why it's a hole is because does it say equal to? No, it does not. So at about 1 2/3, there's a hole. And I'm just going to connect the pieces. And that's the left side of my graph. The right side of my graph comes from the second equation. And this one, at 1, if I substitute in the value of 1, I get -2 plus 1, which is, it's -2 plus 1? -1. So at 1, -1, it's a closed circle. Why is it a closed circle? It's greater than or equal to. So from here, I'm now going to use my slope. My slope is down 2 and right 1, or I can go up 2 and left 1, but I'm heading to the right. So I'm going to go down 2, 1, 2, right 1, down 2, right 1, down 2, right 1, down 2, and right 1, and connect the dot. Oh, pretend that that line touched that. Can't even pretend. So there is my graph of 2 pieces of lines, hence why it's called a piecewise. Okay, notice on the left-hand side, it wasn't easy for me to start at where 1 is because I was going to have a fraction, right? Not an exact value. So I started at the y-intercept and I used the y-intercept to begin my line. On the second one, this was an easy plug-in, right? So I simply substituted 1 in and started from there and utilized my slope to continue the line. Now I can answer questions. If I have f of 0, which side of the line am I using? Well, f of 0 is going to be to the left. So if I go to f of 0, what do I get? 1. So we know f of 0 equals 1. F of 1 is right on the line, right? But I'm not going to use the open circle. I'm going to use the closed circle. And what do I get? -1. F of 2, is that to the left or to the right? It's to the right. If I go to f of 2 and I go down, what do I get? 3, -3. Okay, so you have to know where they fall on that interval of the pieces. So my domain here, is there any break, any point where no x value is defined? Nope, every x value is defined from -infinity to +infinity. So my domain is all real numbers. I have 2 intercepts. One intercept is here at 0, 1. And the other intercept, I would have to find its exact value, I would have to use the first equation and set it equal to 0. So if I have 2/3 x plus 1 equal to 0, that gives me 2/3 x equals -1 multiplied by the reciprocal. So I know that my x-intercept is at -3/2, which I did a pretty darn good job of sketching. I don't know if you've noticed. But my other x-intercept is at -3/2, 0. Now, the range is where this gets tricky. This graph is heading forever to -infinity, but what happens as its highest? What is its absolute maximum? My absolute maximum is right here, right? It's where I cannot equal, was it 2/3? 1 2/3? Yeah, 1 2/3 is my absolute maximum. So the range goes from -infinity to 1 2/3. And is it a bracket or a parenthesis? It's a parenthesis because there's a hole right there. It would have been a bracket if it was closed, but am I closed? No, it is a hole. So I can write it like this, or y is less than 1 2/3. Either way, that's how I would describe my range. So piecewise functions, again, are just literally defined in pieces. There is another example that we could work out, but it's just a larger one, which we can do tomorrow. If you have questions, or you can try, and then there's a word problem we're going to work out. So tomorrow we'll do the example 4 and the word problem, and that will conclude our parent functions in piecewise. Okay. All right.